Hello everyone, this is Shahnawaz Anwer. I am a research assistant professor in the Department of Building and Real Estate, the Hong Kong Polytechnic University. I am going to present my topic titled Comparative Evaluation of Commercially Available and Self-Designed Low-Cost Passive Exoskeletons During Lifting Tasks, a randomized controlled trial. As we know, construction works are the labor-intensive, which include repetitive and physically demanding tasks. Past studies have suggested that construction tasks often involve long working hours, hot and humid work environment, and heavy workloads. Approximately 40% of the construction workers in developed nations showed severe fatigue, which could significantly impact worker safety, general health, and overall productivity. Consequently, large number of construction workers may demonstrate severe level of fatigue that can cause increase in unsafe human action and errors. Additionally, construction workers are prone to develop work-related musculoskeletal disorders and could have increased absenteeism due to excessive fatigue. Exoskeletons are a type of wearable technology that is becoming increasingly popular in construction industry due to their ability to enhance productivity and mitigate safety and health concerns for construction workers. With to the recent improvements in wearable and robot technology, an extensive choice of commercially available exoskeleton suits may now be found in the market. Previous research has suggested that the benefits of exoskeleton suits may vary depending on the particular construction jobs being carried out. While commercial exoskeletons are readily available, there is a growing interest for developing customized exoskeletons that can be tailored to the exact requirements and preference of individual users or work environment. Custom-made exoskeletons have the potential to offer improved ergonomic advantage compared to commercially available ones, as they may be tailored to meet the user's body measurements, specialized tasks, and personal preferences. Therefore, the objective of this study was to evaluate and compare the impact of commercially available exoskeletons versus custom-designed exoskeletons on muscle activity and physical exertion during lifting tasks. The study hypothesized that self-engineered exoskeletons would outperform commercially available exoskeletons in lowering muscle activity and perceived exertion. This is attributed to their tailored design and optimization for the particular task and user requirement. Traditionally, robots are mechanical and bulky, although it provides sufficient output torque. In contrast, current soft robotics are flexible, lightweight, though they have limited power and torque. The purpose of designing wearable exoskeletons are manifold. First, to reduce injury and strain. Second, reduce metabolic rate. Third, to enhance strength and correct body postures. Additionally, exoskeleton devices should be significant and efficient in reducing fatigue, occupational injury, as well as improve productivity. Wearable exoskeletons that are well optimized can aid with body movement during construction tasks. This slide gives structure of our passive wearable exoskeleton systems. There are four straps including shoulder, chest, waist, and thigh to support respective body parts. There are a few springs which store elastic energy during flexion and release energy during extension. There are two pulleys which help wire to move easier. There are two adjustable steel wires which connect shoulder and chest, spring and thigh or knee body parts by hook. Overall purpose of this exoskeleton is to assist the back muscles in material manual handling tasks and static holding position. It utilizes elastic energy that is stored during trunk and knee flexion and released during subsequent trunk or knee extension. This is a 3D model of our exoskeleton. Plate, pulleys, springs, cable and hook all contributed to mechanical function of the system. 30 participants randomly divided into 3 groups, 10 in each group. The experiment was conducted in a laboratory setting. Participants performed symmetric and asymmetric lifting tasks using squat and stoop posture under 3 conditions, that is, no exoskeleton, commercial exoskeleton, and self-designed exoskeleton. The commercial exoskeleton used in this study was the LIVO, and the self-designed exoskeleton was developed by the research team. Outcome measures were muscle activity and physical exertion. Surface electromyography was used to measure muscle activity of the back, that is thoracic and lumbar actor spiny muscle, during the lifting task. Heart rate and the rating of fatigue scale were used to assess physical exertion after each lifting task. Data light Explorer with EMG sensor and Empatica E4 were used to obtain EMG and heart rate respectively. Statistical analysis was conducted using SPSS. Shapreville test was used to assess normality of the data. A three-factor mixed model repeated measure analysis of variance was used to evaluate and compare the results across the three conditions. Post hoc comparisons using the Bonferroni adjustment was conducted. A level of significance was set at P0.05. Descriptive statistics indicate that most of the variables were lowered when performing tasks while wearing exoskeleton system. For example, amplitude of lumbar actor spiny, heart rate, and fatigue scores were reduced. Results of ANOVA indicates that all muscle examined showed significant changes in EMG activity when comparing the primary effects of system. However, there were no main effects of lifting posture and lifting methods. Furthermore, EMG activity for the lumbar actor spiny muscle significantly interacted with the lifting methods and system. However, there was no interaction effect of lifting posture and system was observed for lumbar actor spiny muscle. Interestingly, while there were no interaction effects noted for system and posture or system and lifting method, there was significant interaction effect noted for system, lifting method, and lifting posture. Figure 1 illustrates comparison of muscle activities during lifting methods and lifting postures across exoskeletal systems. This table showed results of fatigue scores as measured by heart rate and subjective fatigue scale. The major effects of lifting method and exoskeleton were statistically significant for subjective fatigue scores. However, changes in heart rate were unrelated to both lifting methods and exoskeleton. There was an interaction effect between lifting methods and exoskeleton for changes in subjective fatigue scores, but not for heart rate scores. Figure 2 illustrates comparison of fatigue scores during lifting methods and lifting posture across exoskeletal system. Figure also represents system usability scores of participants for both the exoskeletal system. As shown in figure 2C, 5 and 7 participants had their system usability scores rated above the criterion for acceptable usability for self-designed and commercial exoskeleton, respectively. The criteria for user acceptability is 70%. While both types of exoskeleton showed favorable results, it was noted that commercially available exoskeletons tended to offer a more reliable and uniform level of assistance and functionality. The exoskeletons were purposefully designed and fine-tuned for the purpose of lifting tasks, considering factors such as the choice of materials, ergonomic design, and user-friendliness. However, self-designed affordable exoskeletons demonstrate promise as economical substitutes, particularly for smaller construction industries or workers with restricted financial resources. The value of self-designed exoskeleton lies in their flexibility to be customized and adapted to meet individual needs and work requirements. It is crucial to acknowledge that the study had certain limitations, including a small sample size and a narrow emphasis on a particular construction task. In conclusion, the key findings of this study are both the exoskeleton system showed promising application as an ergonomic intervention tool to aid construction workers. Findings have provided evidence that the self-designed exoskeleton system is not only practical but also portable, convenient, and user-friendly. And this research may help safety managers select the best passive exoskeleton for use in the construction industry by shedding light on the effect of exoskeleton use on muscle activation and physical exertions. Despite these advantages, more studies are required to determine how these exoskeleton systems affect other peripheral and spinal muscles such as abdominals, physiological metrics such as respiratory rate, oxygen consumption, and task performance across a variety of construction trades. They are the contributors of this study. That's all about my presentations. You are welcome for question if you have. I will try to give my answers. Thank you.